Okay, thanks. I'm going to. Oh, okay, all right. Okay, yeah. So the goal of my talk is to combine two traditions of approach to non-deterministic processes, and then in a manner that is straightforward and general, but that can also capture interesting properties of quantum processes, and in particular non-locality and contextuality. Actually, that is to sort of rewrite and generalize Abramsky and Brandenburg result in their sheaf theoretic approach. So you will see all of the ideas common to Shane's first talk this morning. So okay, so let me get to the first tradition to combine. So the first tradition is to use a Presheaves as a labeled transition system that is labeled by edges of a tree on the base tree. So for instance, take this tree. This can represent Alice having a choice from two measurements, A and A prime. And then you take a Presheaves over that, and then consider, regard the arrows backwards, then this Presheaves represents each measurement having two outcomes. So when Alice chooses measurement A, this could resolve, but also this could resolve. So that's okay. So that's this is the labeled transition system. So the slogan is that the branching in the base tree represents sort of a choice that experimenters make externally to the system, and then the branching in the function component of the Presheaves is a choice that the system internally makes. So you just push a button on the black box, and the black box randomly spits out 0 or 1 for other outcomes. That's the basic idea. And in relation to this slogan, it's sometimes useful to you take advantage of the Presheaves vibration equivalence and consider this Presheaves as a vibration, projecting down those edges to the labels. Anyway, so what we want to do is to assign probabilities to these edges. For instance, to this state S, we'd like to assign vector of probabilities like this. And that is just, we just do that using the second tradition I would like to combine. That is the following. So you take a set of states, sets of states, and then take any relation among them to consider edges as possible transitions. And then you assign probabilities to these edges. Some of them may be, some of the values may be 0, but the constraint is that the probability is normalized in the sense that these add up to 1, these do as well. Yeah. And then the composition of these stochastic relations is given by first connecting the possible transitions to take the longer possible path, right? So S0 can get us to U0, and the probability of that transition or path is given by multiplying the first transition probability and second. Yeah. But actually, there may be several possible paths, but they are all mutually exclusive. So the probability of the entire transition from this one to this one is given by just summing up all these different probabilities. So that's the summary of the composition. So given this composition, let's call this category of such relations RL, or R relations. Actually, this is just a classic category of a certain monad. This is a classic composition of that. So anyway, that's a sort of a more categorical definition. In any case, what I'm going to Actually, yeah, I should say this monad is slightly different from any existing monads in this tradition, like G monad or distribution monad, because it has this weird under some type. But anyway, this tradition I'd like to combine with the first one by first taking a tree of labels, and then instead of taking a presheap over that, I just take a variant functor from that to this category R. Yeah. Then those are possible transitions, and these are all labeled by the edges of the tree. So using this setting, we can represent a bell-like scenario. So these are, as I mentioned earlier, these sort of describe the Allison's and Bob's measurements locally. But let's change their bases this way. Then these composed long presheaves or vibrations represent the same processes as before, except that in this description, Alice's choice is internalized. So what you do is that let the clock tick and then observe Alice choosing A or A prime with the machine speeding 0 or 1. Right? It's just a simple change of perspective. But then using this clock to synchronize the two systems, and that gives us sort of a description of a global setting. But it's just taking a fiber product, or Cartesian fiber product. So it's a sort of a complicated, fancy way of writing down a 16 entry probability table as in Shin's Tom. Yeah. One good thing about this expression is, well, okay, is that there's some sort of a way of characterizing non-signaling using this diagram, because in a nutshell, so take a projection of this guy onto this one, and then this factorization gives the marginalization, the probability of the global to Alice's part. So you can write down that marginalization is independent of both choice. Anyway, this is a more interesting bit. So using this, so given any probability table as in Shane's talk, you can write down a model in terms of this stochastic relational presheave like this. But such a model may or may not be obtained by composing from such a model with this change of base. What does it do? Well, what this change of base does is to forget the middle stage, and we just maintain the information here and here to obtain that one. And what are those states? Those states are just deterministic local variables. So these this guy being obtained in this way means that this model with some probabilities on those edges admits a deterministic local variable model. And actually, we can show by connecting to the Abramsky-Brandenburg result that this condition characterized, or the failure of this condition characterizes contextuality. So this is sort of a local hidden variable models written in transitional terms. Now, what this theorem tells us is roughly the following. So contextuality, it means that the model has to have this shape as opposed to this shape, where this shape means that the system, after sort of the initial preparation, the system chooses a local, deterministic hidden variable, and what we do in measurement is to just read part of the moving instruction set. As opposed to here, you first take measurement context and then randomly. And then after that, the system internally chooses the outcome. So those two, the distinction between those two shapes is what the modal logic is good at, using the vocabulary such as phi will be the case, or phi may be the case after AB, or after A, even conditional probabilities. So let's review how to interpret this language or vocabulary using our stochastic relational Presheaves structure. So first we take a family of trees, of labels. I mean, it's a family instead of one single tree because different labels may live in different trees. So we take a family, but we require that there be an initial tree like this. Yeah? And then we take a stochastic relational Presheaves on top of that. Then this is a sentence that phi will be the case after E will be interpreted in such a way that, for instance, state S after AB means a probability 1 above AB. Yeah, so take a B's, and then the phi will be the support will be a subset of the extension of phi. Yeah? And then after A means probability 1 everywhere above A, so it's probability 1 here, probability 1 here, and so on. Yeah? And then this semantics gives a certain axiom rule. But anyway, good thing is that we can use this model logic to characterize contextuality in logic terms. So let's write det A for this sentence, which roughly, which exactly says that the outcome of measurement A is determined. And then write that for this saying that all the measurements are determined. Okay, then that is actually true at all these states, but not only those states. This characterizes local hidden variables. So this sentence saying that after initial preparation, that will be the case, sort of essentially characterizes local hidden variable models of this shape. And on the other hand, let's consider this description, or partial description of the Hardy model as in Shane's talk. This says that for instance, this part with respect to this model, this part of the sentence says that okay, this cannot be the case, so these paths must have probability 0, but then red edges must have probability 0 because those green are deterministic and probability 1. Similarly, these kill these edges, these kill these edges, but then this part of the description cannot be the case because all these edges are already killed. Right? So the upshot, or in short, this sentence and this description are inconsistent with each other. So the upshot theorem is that the probability table is a contextual if and only if its description in modal-logical terms implies that that may fail. And moreover, it is strongly contextual in the sense of killing all the local hidden variables, as in, for instance, in the PR box, if and only if the description implies that that cannot be the case. So this is pretty much it. But in conclusion, I'd like to say that this framework sort of rewrites the Brandenburger result, but also adds more flexibility and generality in terms of both internal and external structure of the non-deterministic processes. So, thank you.
Say a bit more about this flexibility you just mentioned. So what do you envision as being possible here?
Oh yeah, okay, good question. For instance, you don't have any restriction, not much restriction on the shape of what the process of external choices. You can just take a sequence of long sequence of quantum protocols instead of just take a measurement context and then take a power set of that. That's what the Abramsky Brandenburger do. right? So that's one flexibility here. Another flexibility is that you can take all shapes here. So this is in their sheaf theoretic approach, what they do is restriction, but you don't have to have restriction necessarily. So that's external. Another thing is that they, so another thing is that this is sort of, what they do is sort of assign probabilities sort of vertically. What I do is horizontally, and you can show that they sometimes you can so from any horizontal assignment you can recover the vertical assignment, but not all. Okay, so it's but not the other way around. So you can sort of express many more cases with the horizontal assignment as opposed to the vertical assignment. So that's another generality that comes in. Yes.
You had you said non-standard combination of the power set and distribution model?
Yes, yes.
Are you claiming that your combination is a monad?
Yes, yes, it's a monad. Yes. It really follows from the distribution monad being a monad. Kind of rather straightforward. Oh, sorry, I passed. Yeah. I can send you a note. Yes. Yeah. It's yeah, because it's just you take a sort of so the product and the